Okay. So, today we will look at extrema of real valued functions. So, E is a non-linear space, U contained in E open, and now I look at f of u in E going into R. So, these functions are all real valued. So, then we can talk of maximum value, minimum value and all that, because once you are in R, you have order relation and therefore, you can compare. So, we say that f has a relative maximum respectively minimum at A in U if there exists a neighborhood V of A such that for all x in V, f of x is less than or equal to f of u and f of A, respectively f of x is greater or equal to f of u. So, relative means it is not global, global means everywhere, relative means in a neighborhood. Okay. So, nearby everybody is bigger than this or everyone is less than this. So, we want to know what are the conditions a function satisfies assuming differentiability. So, what do you know in one dimension? If f is from R to R or from an interval, then when do you say it has a relative maximum or minimum? So, the first condition is that, so f is from R to R. So, if it has a relative x maximum or minimum of A, the first condition you will put is f dash A equal to 0, and then that is not enough. So, you will then go and investigate the second derivative. If the second derivative is positive, then you say it is a minimum. If the second derivative is negative, then you say it is a maximum. If the second derivative is 0, then you can't say anything, it is a point of inflection and it is neither a maximum nor a minimum. Okay. So, we want to know how these things generalize to our situation when you are dealing with a nonlinear space or even let us say Rn. Okay, Rn is okay. So, the first theorem is clear. So, I will always assume these three things, I will not write it every time. Okay. So, f has a relative extremum, I will say extremum meaning maxima or minima, I do not want to, okay, at A in U, f differentiable at A in U implies f dash of U A equal to 0. So, the result we expect continues to hold. So, the derivative is still 0. So, how do you prove this? So, what should I now, whenever you have a real valued function, the derivative at any point belongs to L of E R. So, this is the dual space. So, the derivatives are all continuous linear functionals. Okay. So, when I say derivative is 0, it is a functional which is 0, that means its action on every element has to be 0. So, let V in E be arbitrary to show f dash of A acting on V equal to 0 for every V. This is what we want to show. Okay. Then we say that if a functional is 0 at all points, then you say it is a 0 functional. Okay. So, that is what we mean by saying it's okay. So, you have this. Now, A belongs to U, U is open. So, there exists an interval j open interval in R, j which will be some minus epsilon to epsilon of this form, such that A plus t times V belongs to U for all t in J. So, this is an open set here. So, I have a point A here. So, V is some other direction. So, A plus TV is this vector here, okay. And so, because it is open, so in this direction some part is going to lie inside, okay, because there is a ball surrounding it. So, if you take in any direction and draw the line in that direction, it will be intersect this ball. So, it will intersect for some. Of course, the length of this interval will depend on V, but that does not matter for us. Okay. So, now you define phi of t equals f of u plus t times. Then by the chain rule, phi is differentiable at the origin, and so phi dashed of 0 is f dashed at u times derivative of this, which will give you v. So, I am just applying the chain rule. So, f dash of u plus tv. So, phi dashed of t equals f dash of u plus tv into v. So, we just apply t equal to 0, and therefore, we get this. Now, because u is a relative, let us say minimum. So, let u be a relative minimum. Now, what do you know about phi dashed of 0? This can be written as limit as t goes to 0 plus of phi of u plus phi of phi t minus phi 0 by t, and it is also equal to limit as t goes to 0 minus phi t minus phi 0 by t. That is the derivative. Whatever direction you approach, it has to give you the same. Now, what is phi of t? Phi of t is f of u plus tv, okay, and therefore, f of u plus tv is greater than or equal to f of u for all t in the interval. Because it is a minimum, if you take any neighborhood point, the value will be more, and therefore, it has to be greater than or equal to this. So, let me now look at this. Phi of t will be, therefore, phi of t is greater than or equal to phi of 0. So, this is always non-negative, denominator is negative. So, this ratio is always negative, non-negative and negative. So, this is negative. So, if I take the limit, it will still be negative. So, this is less than or equal to 0. Here it is always non-negative, denominator is also non-negative. So, the ratio is non-negative. So, the limit will also be non-negative. So, you have 0 greater than or equal to phi dash 0 greater than or equal to 0. So, this implies that phi dash 0 equal to 0, that is f dash u acting on v equal to 0. And this is true for every v, you can do this, and therefore, that is f dash u is v arbitrary. So, if f is from u contained in Rn going into R, what do you mean by saying f dash of a is 0? Oh, I have put u there, sorry. Sorry for this, okay. This A everywhere. Oh. It's A. So, what do you mean by saying f dash of A? We already saw if it is a function from Rn to R, how is the derivative given? Derivative is a vector whose components are the partial derivatives. So, df by dx1 at A, df by dxn at A, and which I call as the grad f at A. So, if this is 0, that means all of these have to be 0. So, this is the condition which you already know. So, if f has a relative extremum at A, you have df by dxi at A equal to 0, 1 less negative I less negative. So, this is the standard condition. So, now we want to know what happens, how do you decide if it is a maximum, if it is a minimum, or it is neither of these two. Okay. So, for that we need to go to the second derivative. F from u contained in E into R differentiable on u, that means is differentiable at every point of u, and twice differentiable at A. Assume f has a relative minimum A. So, then you already know f dash of A has to be 0. Okay. Then f dash of A equal to 0, and for every v in E, f double dashed of A, this is a bilinear form, yesterday we saw. Okay. So, it will act on two variables. So, apply it to V twice. This has to be greatly equal to 0. So, when you had a minimum in one dimension, you said second derivative is positive or non-negative, right. So, that is translated in this fashion. It is a bilinear form whose action on v comma v is greater than or equal to 0 for every v. Okay. So, let v be in E arbitrary, then A plus T v belongs to U for T small. We already saw this, even in the previous example we saw this. So, look at f of A plus T v minus f of A. Because it is a minimum, this is greater than or equal to 0, because because it is a relative minimum. So, nearby points it will all be bigger. Now, let us write the Taylor expansion of this. So, it will be f dashed of A times T into TB, f of A plus H minus f of A is f dashed of A H plus 1 by 2 f double dashed at A at TB plus little o of T square. So, that is the Taylor expansion, first theorem which we proved. Well, f dashed of A is 0. So, this term goes away. This is a bilinear form. So, I can pull out the T. Okay. So, 0 is less than or equal to T square by 2 f double dash A VB plus little o of T square. Now, divide throughout by T square by 2. So, this goes off. So, this will be 2 times this by T square. Inequality will not change. I am dividing by a positive number. Now, let T go to 0. So, left hand side is still the same. Right hand side, this is independent of T. So, this will give you f double dash A VV. Definition of little o means this goes to 0. Okay. So, that is what we wanted. So, what is the theorem if I have a relative maximum? F double dash A VV should be less than or equal to 0 for all V. So, that is the condition for maximum. So, remark relative maximum if f dash A equal to 0 and f double dash A VV is less than or equal to 0 for all V. So, let us see what happens in the case of Rn again. So, what is f double dash A? It is acting on any x comma y, will be x transpose y into some matrix here. And what is that matrix? It is a matrix of second partial derivatives. So, you will have d2f by dx1 2 at A, d2f by dx1 dx2 at A, d2f by dx2 dx1 at A, d2f by dx2 2 at A. So, this is that matrix which comes here. And yesterday we proved that these two are equal. Okay. So, it is a symmetric matrix. So, we have now we are now in linear algebra. If A is a symmetric matrix, what do you know about its No, what were you saying? Diagonalizable. Okay, that is what we want. Okay. So, if I write this, then you can. So, when will this be greater than or equal to 0? So, we want x transpose Ax to be greater than or equal to 0 for all x. Exactly. So, all eigenvalues are greater than or equal to 0. So, if this happens, then you have a relative minimum. If all the eigenvalues are less than or equal to 0, then you will have a maximum. Okay. And if the eigenvalues are mixed, then we can't say what happens. Okay. So, let us take very simple example. So, this is how you compute in so R, I have taken R2 to R here, okay, but its Rn to R is the same thing. Rn means you have many more, it is a n by n matrix, you have all kinds of partial derivatives. It is still a symmetric matrix, and therefore, if all the eigenvalues of that matrix are positive or non-negative, if they are strictly positive, then it becomes a strict maximum or strict minimum. I will come to that here. So, let us see this example. So, f of x y is ax square plus by square. So, if you take fx, that is 2ax, fy is 2ay, partial derivatives. So, this is 0, this is 0 means x equals y equals 0. So, the only critical point is the origin. Okay. So, if a and b are positive, then or non-negative if you like, then this is always non-negative, and therefore, it has a minimum at the origin where the value is 0. If both of them are negative, then that expression is negative, and so it has a maximum at the origin where the value is 0. Suppose one is positive, one is negative, then you have a function like x square minus y square. Okay. So, at the origin f of 0 0 is 0. If you take f of 0 y, then this is negative, f of x 0, this is positive. So, 0 is neither a maximum nor a minimum, because in any neighborhood of the origin, there are points here where the function is positive, there are points here which the function is negative, and it is 0 at the origin. So, origin is neither a maximum nor a minimum value. Okay. So, when the second matrix of second derivatives has mixed eigenvalues, then you can say nothing, but if they are all positive, then you have a minimum, if they are all negative, then you have a maximum. If they are strictly positive, then you say it is a strict minimum. That means, in a neighborhood, this is the only point which will have the minimum value, all others will be strictly bigger than that. Okay. So, this is about maxima minima without constraints. Now, we want to look at maxima minima with constraints. So, extrema with constraints. So, f u to e to r is some given function, and phi is also some other function. So, we want to find out what is the maximum value of f or minimum value of f such that phi of x equal to 0. such that. So, on the curve or on that manifold phi f x equal to 0, you are to find maximum and minimum values of that function. So, now you can't say f dash equal to 0, because when you have an open set available, then you have all directions V with which I can do things. But now I am allowed to move only in that subset, and that is in fact, if it is a continuous function, this is even a closed subset. Okay. So, I do not have all directions available to me because there is no openness, and so that first theorem which I proved cannot be proved now, because as we said, take V arbitrary. Now, no longer V can be taken arbitrary, okay, because if you take A plus TV, this we could do and work with this, but then why will this be 0? This may not be 0. Okay. So, all that theorem which we do, so the vanishing of the first derivative is no longer true. So, how do we find out the candidates which will tell you whether it is a maxima or minima? Okay. So, all extrema problems are two steps. First, you look at the candidates which qualify for the extrema. So, that is given by the vanishing of the first derivative or something working with the first derivative. But afterwards, you have some more work to do, namely you must check if it is a maximum at all or a minimum at all by some other argument. In the case of the without constraints, then we gave one in terms of the second derivative. But if the second derivative does not exist, then of course even that is not there, you have to somehow some other method you have to check. So, there is always a second checking which is you have to do. Very often we do not do it because you know, so in the exam if they ask find the maximum volume of some sphere which is doing something, okay, we get the extremum and we know, okay, so that has to be it. I mean, but actually you have to check that that is really a maximum. Okay. So, before I do something more general, let me just do with two variables. Okay. I will do something with two variables, give you a theorem, and then we will see how to generalize this. Okay. So, let f of x y g of x y be differential. So, we are now E is R2 differentiable and A B is a point, be differentiable in a neighborhood of A B. Then we look for max max or min of f of x such that g x is a constant, or max min g of x such that f x equals constant. We are looking at one of these problems. Okay. So, if the constraint equation, namely this one or this one, defines one variable as a differentiable function of the other, then something happens. Okay. What do I mean by this? So, this is what we did yesterday, implicit function theorem. Okay. We have g of, sorry, I should put f of x y because I am in two variables. So, if I say g of x y equals constant, then what did we see yesterday in the implicit function theorem? Whether we can write y equals some phi of x, so that you have g of x phi x equal to 0 as the only possible solutions of this equation in the neighborhood of the point you are interested in. Okay. When was this possible? If the second derivative of g with respect to at a b is an invertible mapping. That was the content of the implicit function theorem. So, here I am saying either this should be possible or x should be written as psi of y. So, psi of y equal to 0. One of these two I should be able to do. That means either the derivative, partial derivative with respect to x must be invertible, or the partial derivative with respect to y must be invertible. In this case, invertible means non-zero, that is all, because the partial derivatives are all numbers. We are in R2. So, the partial derivatives are linear maps from R to R, which are just numbers, okay. And therefore, either one of the partial derivatives is not 0. That is the equivalent way of stating this last condition, okay. So, then what happens if there exists a relative extremum at a b? We have determinant of df by dx at a b, df by dy at a b, dg by dx at a b, dg by dy at a b equal to 0. Okay. So, this is the theorem, and from this condition, so instead of taking the first derivative equal to 0, if you, this will give you a condition which will tell you how to find the points a and b. Okay. So, let us prove this. So, let us fix an example. Okay. So, we are taking relative extremum of f of x y such that g of x y equals constant. Okay. All other cases you can do similar, and we assume g of x y equals constant. This is the same as saying g of x some phi of x equals constant. That is, one variable can be expressed as a function of the other. Okay. So, let us differentiate this relationship. So, you get dg by dx at a b plus dg by dy at a b times phi dash x equal to 0. Right? I am differentiating with respect to x. So, we have done this several times, implicit differentiation. So, when you have a function inside, chain rule tells you you should get dg by dx plus dg by dy times phi dash x. Okay. Now, f is now a function of, if you restrict it on this manifold now, so I have to look at x comma phi of x, because if I want gxy equals constant, y must be equal to phi of x. So, I only need to look at this function. Now, this is a function of one variable, there is no constraint for you. I got rid of the constraint by plugging it into the equation. So, I can say that the first derivative must be 0 for this, because it is a relative extreme. So, what is the first derivative? df by dx at a b plus df by dy at AB times phi dash AB. Equal to 0. So phi dash what? B. Okay. Phi is a function of y is a function of x, so this phi dash t. Sorry. Okay. I am differentiating with respect to x and taking the derivative at a. So, I get df by dx at AB plus df by dy AB phi dash j equal to 0, and this I differentiated this equation that same way and got this. So, look at these two homogeneous linear equations. What is the matrix? Df by dx at AB, df by dy at AB, dg by dx at AB, dg by dy at AB, multiplied by 1 phi dash ta equals 0. I am writing it matrix form, right. So, I have a matrix here, applying it to a vector which is non-zero because there is 1 here, I get 0. So, this is in the kernel of that matrix. So, the determinant has to be 0. If you have a non-zero solution to the homogeneous linear system, then the determinant of the matrix has to be 0. So, we get this determinant is. So, let us I will illustrate it with example. We will do probably some more in the afternoon, but let me give you an example. So, find the rectangle of maximum area inscribed in an ellipse with the sides parallel to the axis. So, I have an ellipse here. So, I need that the 4 corners of the rectangle should be and the line should be parallel. So, that means these 4 points must be symmetric to each other because they should be bisected by the axis. Okay. So, if this point is x comma y, what is the area of the rectangle? It is 4 times this area. So, it is 4xy. And x and y should lie on the ellipse. So, you have x squared by a square plus y squared by b square equal to 1. So, what is our problem? Maximize f of x y equals x y, because 4 does not matter. If I maximize x y, the 4 is a constant, it does not matter, such that x squared by a square plus y squared by b square equal to 1. So, we have two functions. Okay. So, if x and y are positive, they better be positive, otherwise you will not get a rectangle. Okay. So, if x and y are positive, then of course, I can express any of these as a function of the other, it does not matter. I can express y as a function of x or x as a function of y and in the neighborhood, and therefore, there is no problem. Consequently, I can write those two conditions. So, if I take the derivative df by dx is y, df by dy is x, then you have 2x by a square, 2y by b square. This determinant must be 0. I am just writing that condition there. Anyway, the 2 can go away because, so you get, if you write the determinant, so you get y square by b square equals x square by a square. But the sum should be 1, so each must be equal to 1/2. So, the candidate for maxima or minima is when this happens, that means x equals a by root 2, y equals b by root 2. So, I have identified where I have to look for the solution. Now, how do I know it is a maximum or a minimum? Now, minimum does not exist fortunately, because I can always draw a rectangle very close to the to the major axis or very close to the minor axis, then x or y can be made go to 0, and so the infimum is 0, that is never attained. Okay. The infimum is 0, but you do not have a rectangle which does it. Okay. So, this critical point must only give you the maximum, because every continuous function there is a maxima and a minima definitely in a compact set. Ellipse is compact. So, see so many arguments I am using. Okay. Ellipse is compact. So, this rectangle function of x y as x y goes on that is a continuous function. Therefore, there is a maximum, there is a minimum. The minimum is reached, I know where it is at these points, because the value is 0. So, when we are looking at x y positive, then the maximum only will be reached. So, this is a maximum. So, the maximum area is 4 times this. So, maximum area equals 4 times a by root 2 b by root 2, which is 2a. So, you do not have this condition that the first derivative vanishes, but that is replaced by some other condition where you bring in the 2. Okay. And there is a symmetry, whether you are looking at this problem or whether you are looking at this problem, the answer is the same. So, that is called duality. So, you can maximize subject to the other one being constant or minimize. So, if for instance, if you take all curves which enclose a fixed area, what is a minimum perimeter? It is a circle. The answer is the same if you take all curves which have the fixed perimeter and maximum area inside. Okay. So, fix the perimeter, maximize the area, or fix the area, minimize the perimeter, the answer is the same, it is always a circle. Okay. So, like that. So, you have this duality, namely when you have a constraint you can interchange the two, the candidates will be the same, the values will not be the same, but the candidates where you have to look for the extrema are the same. So, now let us look at more than 2 variables, then what happens? F of x1 xn, g of x1 xn differentiable, and we are looking at relative extrema of f such that g equals constant, or relative extrema of g such that f equals constant. So, let AB be a point of relative extrema of one of these two problems. Then you look at and also assume in the constraint equation one variable can be expressed as a differentiable function of the remaining variables. What do I mean by this? If I have g of x1 xn equal to c or 0, let us say, then I can write xn as a function of x1 to xn minus 1, such that you have g of x1 xn minus 1 phi of x1 xn minus 1 equal to 0, and these are the only solutions. Again, you will recognize that this is a condition which comes from the implicit function theorem. Then consider the matrix f df by dx1 at AB, A1 AN. No, this is not AB, okay, it is not in 2 dimensions, we are in A1 AN. df by dxn at A1 AN, dg by dx1 at A1 AN, dg by dxn. Look at this matrix. Then every 2 by 2 submatrix of this will have determinant 0. Okay. So, you have a 2 by something. So, any, that means the rank of this matrix is 1. So, should be a matrix of rank. That means these two are linearly dependent rows. So, any. So, let me prove this when n equals 3. I mean, the proof in general case is identical. So, let us assume that g of x y z equal to 0 is the same as saying g of x y phi of x y equal to 0. So, now the proof is exactly like last time. Okay. So, you assume ABC is a relative extremum. So, if you look at f of x y, phi of x y, this function is such, these points are such that this happens. Okay. So, this there is a relative extremum for this at AB, but now there are no constraints, and therefore, you can say the first partial derivatives have to be 0 with respect to x and with respect to y. So, you have df by dx at ABC plus df by dz at ABC times d phi by dx at ABC equal to 0. Similarly, df by dy plus df by dz times d phi by dy equal to 0, because the partial derivatives with respect to x and y of this function have to be 0, because now we are having a relative extremum without constraints. The constraint has already been incorporated. Then you differentiate this equation with respect to x and y again. So, you get dg by dx plus dg by dy d phi by dx equal to 0. Similarly, dg by dy plus dg by dz d phi by dy equal to 0. So, you now look at this matrix df by dx, df by dy, df by dz, dg by dx, dg by dy, dg by dz. Now, take these two equations. Then corresponding to the matrix which is consisting of these two columns, 1 d phi by dx is a solution of the homogeneous system, and therefore, that determinant has to be 0. Similarly, if you took the second pair of equations, that means this one and this one, these two columns have 1 and d phi by dy as a solution, and therefore, that determinant has to be 0. And that means these two are linearly dependent, these two are linearly dependent, that means these two are also linearly dependent. So, any 2 by 2 matrix will have determinant equal to 0. So, that is how you write that condition. So, let us see under an example of that. Find the minimum volume of a tetrahedron formed by a plane passing through a fixed point x1, y1, z1 and making positive intercepts on the coordinate axis. So, you have the coordinate axis, you have a plane which makes positive intercepts on the coordinate axis and it passes through some fixed point x1, y1, z1. So, you want to find the volume of this tetrahedron which is there. So, if R, S and T are the intercepts, then what is the volume of the tetrahedron? Volume of the tetrahedron is 1 by 6 times RST. So, RST intercepts. So, that is the formula for the volume of the tetrahedron is 1 by 6 RST. And what is the condition? That the plane must pass through x1, y1, z1. What is the equation of the plane which passes, which makes intercepts r, s and t? It is x by r plus y by s plus z by t equal to 1, just like straight line which makes intercepts a b, so is x by a plus y by b equals 1. Similarly, a plane which makes intercepts r s t is x by r plus y by s plus z by t equals 1, and it should always pass through x 1. So, this is the condition. So, you want to maximize, so you want to find minimize r s t such that x 1 by r plus y 1 by s plus z 1 by t. Now, why will I get a minimum this time? Maximum is infinity, because if I say take t very close to z1, then this is almost 1, then these two have to be 0, almost 0. That means r and s will be very, very big. So, r and s will be very big, t will be very close to z1. So, that means the volume can be made as big as you like by taking. Okay. So, the maximum is infinity, which is not attained. So, whatever condition we get from this method will be give you the minimum value. So, we have to write down those three things. So, differentiate with respect to, so forget this 1 by 6, okay, I have already done that. See, if I differentiate with respect to r, I get st, then rt, then rs. That is the first row. Then here I will get 1 by r, minus x1 by r square, minus y1 by s square, minus z1 by t square. This is the matrix I get by differentiating like that. Now, I take any 2 by 2 submatrix, that should give me 0. So, let us take the first two, these two for instance. So, if you take that, so this will give you this t can be cancelled because it is common. So, you get minus x 1 by r equals minus y 1 by s. So, you get x 1 by r equals y 1 by s. If you take these two and write down the determinant, now r is common in this, so you can get rid of it. So, T s and this, so you get y 1 by s is z 1 by t. And they add up to 1, so each has to be equal to 1 by 3. So, r must be 3 x 1, s must be 3 y 1, t must be 3 z 1. So, the maximum volume is 1 by 6, 3 x 1, 3 y 1, 3 z 1, which will be 9 by 2 x 1 y 1. It is the maximum volume, minimum volume. Okay. Maximum is infinite. Is it clear the method? So, this is tells you how to find out the places where you have to check for maximum minimum. So, this method gives you like this. Okay. So, all this R2, R3 we can write do one by one, but there is a general result which tells you how to handle this, not only with one constraint, but with many constraints. Okay. It is called the method of Lagrange multipliers. E is a Banach space. So, we need completeness because I am going to use the implicit function theorem. So, I will need completeness. Phi belongs to C1 of ER. What does this mean? Phi is a mapping from E to R, which is continuously differentiable. Okay, then I put C1. C1 means continuously differentiable once. K equals set of all V in E, so set phi of V equal to C. Assume for all V in K, phi dash of V is not 0. So, this condition is similar to saying that one variable can be expressed in terms of the other variables. So, that is the generalization of that condition, because anyway I am going to apply implicit function theorem and therefore, this will be needed. Okay. Let u in K be such that f of u is the minimum of f of x in K. Then there exists a lambda in R such that f dash of u equals lambda times phi dash. Okay. So, this last condition is saying that these two rows are linearly independent. Okay. So, that is why every 2 by 2 submatrix had 0 determinant. That means, these two rows, this matrix has rank 1. So, that means, these rows are linearly independent, and that is what I am stating here in this. Okay. Linearly dependent, thank you. Yeah, linearly dependent, they are linearly dependent, that is why they did it. So, proof. So, u belongs to K. So, phi dash of u is not 0 because of the assumption. Then but what is phi dash of u? Phi dash of u is a linear functional, right? Phi dash of u belongs to L of ER. So, this is nothing but E dash. It is a continuous linear functional. So, what do you mean by saying a continuous linear functional is not 0? That means, when you act it on some non-zero vector, it should produce a non-zero number. At least there must be one such vector. Okay. So, then there exists W naught such that norm of W naught equal to 1. This is just saying it can be any number you like. I am just saying it because I want W naught to be not 0, and phi dash of u acting on W naught is not 0. That is the meaning of that statement. So, let E naught be the kernel of phi dash of u. Phi dash of u is a linear map from E to R, and therefore, it may have a kernel. Okay. It will have a kernel. Why? Y will say E is a Banach space. So, let us assume dimension is at least 2. Kernel anyway, there is a 0 in the kernel, but other than 0, suppose I have an n dimensional space and I have a linear functional what will be the dimension of the kernel? N minus 1 by the rank nullity theorem, because the range is 1. So, this has to be at least n minus 1. So, this is definitely there. It is in infinite dimensional space, it is even an infinite. So, I can write E as E naught direct sum R W naught, because the range always has codimension 1. I mean the kernel always, you just now said if you have n dimensional space, the kernel is n minus 1 dimensional. Okay. So, plus 1 dimension gives you the whole space. So, I can always write E as the direct sum of E naught, which is the kernel, plus this constant multiple times W naught, the one dimensional space generated by W naught, because that is not 0, that will not be in the kernel. So, now I am going to define phi of from E naught cross R to R. So, phi of V t is small phi of V, U plus V plus T W naught. U is that fixed point which I am talking about, where I have a relative extremum, and then V is in the kernel and T W naught is, because every element can be written in this way. Okay. So, what is phi of 0 0? It is phi of u, but phi of u is also 0 because u belongs to K. Now, what is d phi by dV at 0 0? So, d phi by dV at 0 0 is a mapping from E naught to R, right. When you have a partial derivative, it will go from the corresponding space to R. That is how we have defined partial derivatives. And what is that equal to? So, acting on any H. So, I am just differentiating with respect to phi here, V here, by chain rule, that will give me phi dashed at u, because I would put V equals T equals 0, and then V is just that. So, it is just the identity map. So, I will just get H. So, I use chain rule, but where is H? H is in E naught. What is E naught? E naught is the kernel of phi dash u, and so forth. This has to be 0. So, for every H this is 0, that means d phi by dV at 0 0 is 0. Then what about d phi by dt? So, again I apply the chain rule, and now I have to differentiate with respect to t. So, I get, if I apply chain rule, I will get phi dashed at all this, but if I apply 0 0, I will get again u, and if I differentiate with respect to t, I get w naught, and that I know is not 0. So, I have all the apparatus necessary for applying the implicit function theorem. I have, this is one dimension and the derivative with respect to this variable is not 0, that means it is invertible because it is one dimension. Okay. So, I can apply. So, I want, you see, we in the previous theorems we said one variable can be written in terms of the other variables. Okay. So, now that is exactly applying the implicit function theorem to incorporate the constraint equation into the original equation. Okay. So, by implicit function theorem, there exists a neighborhood u of E naught v, let us say v of E naught, v of 0 in E naught, and a differentiable function zeta from v to r such that zeta of 0 is 0 because we are at 0 0. So, 0 must go to 0 and zeta dashed at 0, yesterday we wrote a formula, it is the inverse of this into the derivative of this, but this derivative is already 0. So, that is also 0 and phi of u plus v plus zeta of v w naught equal to 0. So, we want phi of some v to be phi of something to be 0. Okay. I am taking all vectors of the form u plus v plus t w and I am solving for t in terms of v, and so that is zeta of v. So, all solutions of this equation are given like this. So, you now look at this function f tilde of v is f of u plus v plus zeta v times w naught. So, I am doing exactly what I did in the earlier theorems. I first solve for the constraint equation, express one variable in terms of the other, make that substitution into the original function. So, here I put t as zeta of v. So, I express t in terms of v, so that all these elements are always satisfying phi of the constraint. Now, I substitute for that here. So, this has a relative minimum at 0, relative, yeah. That means f tilde dash of p at 0 is 0. So, for every v in E0, f tilde dash 0 acting on v has to be 0. But what is this? So, what is f tilde dash at any point v? It is f dashed at u plus v plus zeta v w naught acting on, then you have to differentiate this with respect to v. So, if I differentiate v with respect to v, I get identity plus zeta dash v w naught. So, that is the 0, this is 0, zeta v is 0, zeta dash v is also 0. So, you get that f dashed of u acting on v equal to 0. So, what is the conclusion now? What is E0? E0 is the kernel of phi dashed. So, if phi dashed of uv equal to 0, so that implies that f dashed of uv equal to 0. Now, we have a nice problem in linear algebra again. So, V is any vector space, and let us say G and H are two linear functionals. And kernel of G is contained in kernel of H. Okay. So, that is exactly the situation. I have a vector space which is E, and I take anything in the kernel of phi dash u, and I am proving that it is in the kernel of f dash u. So, the kernel of, okay, then H must be equal to lambda h. Okay, so this so let us see how to do this in linear algebra. So, V is a vector space. So, now I define a mapping from V to R2. X is going to Hx, Gx, Hx. Okay. And this is non-zero linear functionals, or two non-zero, then only, otherwise if one of them is 0, then you have nothing. So, this is a non-trivial subspace. The range of this is a non-trivial subspace of R2. Okay. Now, can you give me a point which does not belong to this subspace? Range of T, let us say, range of T. So, let us say, okay, kernel H, kernel, this is, then only this will come. Okay. Yeah, yes, 1 comma 0, very good. So, if h of x is 0, then g of x must automatically be 0, because that is the condition which we have given here. Okay. But if g of x is 1, that is not possible. Okay. So, this point cannot be in the range. Okay. Now, what is so the space is a one dimensional subspace, the range is a one dimensional subspace. Now, what is a one dimensional subspace in R2? A straight line passing through the origin. So, it must be of the form alpha x plus beta y equal to 0, and 1 0 is not on that subspace, that means alpha is not equal to 0. If I apply 1 0 here, I get alpha, that point 1 0 is not on the straight line. So, alpha cannot be 0, okay. But all these points are on that line, right. So, alpha times g of x plus beta times h of x is 0 for all x in V, because they are all points on that line, that is the range. So, from this you get g of x equals minus beta by alpha times h of x. Okay, that is the lambda. Okay, so I will give you exercise. Try this. This again exercise only in linear algebra. It has nothing to do with what I am doing, but I want to use it. Okay. So let us take V is any vector space, and F naught, F1, Fn are linear functionals on V. Okay, such that intersection I equals 1 to n kernel of Fi is contained in kernel of F naught. Okay. So, this is a particular case of that general result. If I take n equals 1, I have this. Okay. If I have n equals 1, there is only one functional, so there is no intersection. So, I have this. Okay. This is saying, so what does this say? This means if Fix is 0 for all I equals 1 to n, then F0x also has to be 0. So, it is the same thing. Then F naught equals sigma lambda I Fi. There exists lambda I 1 less equal to I less equal to n such that F naught is a linear combination of the Fi's. Proof is almost identical. So, it is instead of R2 you get a map to Rn and then take a point which is not on the image, then you have to apply Hahn-Banach theorem or something like that, and then you. Okay. So, from this it follows, from that linear algebra result, it follows that f dash u equals lambda times phi dash. And now, using this exercise, I will immediately tell you so let E be a non-linear space, phi I are C1 maps from E to R, 1 less than equal to I less than equal to m. So, now there are m constraints and k is set of all v in E such that phi I of v equal to 0, 1 less than equal to I less than. So, u in k relative minimum of f on k, and you assume that phi dash of v, phi I dash I equals 1 to m are linearly independent for every v in k. So, when I add only one constraint, I said it is non-zero. When I have m constraints, I say that these vectors are all linearly independent. Then there exists lambda I 1 less than equal to I less than equal to m such that f dash of u equals sigma lambda I phi I dash. So, these are called these lambda i's are called the Lagrange multipliers. So, how is that? So, give me just 2 minutes, I will say this and we can go. So, let us take again R into R. And you want to find relative extremum of f such that phi I of v equal to 0, 1 less v to I. So, you have m constraints. Okay. So, what I am going to do is I define the Lagrangian now, which is f minus sigma lambda I phi I. Okay. So, now this is a function of the variables of f as well as this lambda 1, lambda 2, lambda n, which are the unknowns now. Okay. And this last condition there tells me that df by dx1 minus sigma I equals 1 to m lambda I d phi I by dx1 equal to 0. Then df by dx2 and so on, df by dxn. So, you get n equations, but you have n plus n unknowns now. You have the n unknowns f1, x1, x2, xn, and now I added these extra unknowns. So, I need m more equations, but they are already there because they are phi 1 u x equal to 0, phi 2 x equal to 0, phi m of x equal to 0. So, this gives you these, they have to be satisfied anyway. So, you have the m constraint equations and these equations given by this theorem. So, if you solve all these together, you will get the candidate where you have to search for maxima or minima, and then you do further tests or something to convince yourself this is a maximum or that is a minimum. So, we will see example of this in the afternoon. It just does not matter, you can put what you like, because if you put plus, then the lambdas will all come minus of the correct value. I mean
C1 means continuously differential. That means the differentiation is continuous.
Yeah, that is, see, for each x I get f dash x. This belongs to L of EF. Okay. Then you look at the map x going to f dash x. This is now a map from E to L of EF. Both are non-linear spaces, and now you can say is this map continuous or not.
So, f dash is continuous.
Yeah.
So, shall we mean f dash exists?
No, every continuous function is not differentiable. No.